Welcome to the ninth part of the series of lecture related to the RM software for filter design. Here now we will discuss the synthesis of analog filters, analog transfer functions, obtained by transformations of low-pass prototypes. Three transformations will be considered: low-pass to bandpass, low-pass to high-pass, and low-pass to bandstop. The low-pass to bandpass transformation is given on the left-hand side, where S is the complex frequency. In the prototype domain, omega 0 is the bandwidth of the low-pass filter, or the cutoff frequency of the low-pass filter. On the right-hand side of this equation is Z, which is in the S domain new notation for the complex frequency, for the bandpass filter. Omega C is the central frequency of the bandpass filter, and BR is the relative bandwidth of the bandpass filter. It stems from the original omega domain, on the real axis domain, transformation, which is shown on the right-hand side, where capital omega is now the frequency of the bandpass filter. The low-pass on the left and the bandpass on the right frequency mask are shown on the right-hand side of this slide. This transformation produces a bandpass filter which has geometrical symmetry, which means that the central frequency, omega C, is obtained as a root of the product of the new passband edges frequencies, omega L and omega U, omega low and omega up. As one can see, the values of the maximum passband attenuation and minimum stopband attenuation are retained, while new values of the edges of the transition region are obtained, which are not controlled directly and indirectly. Here is an example. Of the left-hand side is a set of zeros on the top part of the table and poles of the lower part of the table of an eighth order filter with 6 transmission zeros. 4 of the transmission zeros are on the omega axis and 2 are complex. On the right hand side, this table is visualized so that the red squares are zeros and the blue rhombs are the poles. This is the low-pass prototype. The bandpass filter, which is obtained by this transformation, now is 16th order doubles with 14 transmission zeros. In this case, we used a central frequency of to be 1 radian per second and the relative bandwidth to be 0.4. Everything is doubled as look into the number. And here is the pattern of the new poles and zeros, as one can see, symmetrically around 1 and minus 1, or around omega c and minus omega c, practically is repeated the low-pass prototype. We have it up and down, and as one can see, new transmission zero is created in the origin as counterpart of the zero which is at infinity. Here is the attenuation characteristic of the bandpass filter. One can easily recognize that there is no arithmetic symmetry when looking to the passband, and that the symmetry is geometrical. That was done, this example was purposely chosen with broad passband, relative bandwidth is 0.4. The difference between arithmetic and geometrical symmetry will diminish if the relative bandwidth is decreased. This is the phase characteristic of the bandpass filter obtained by the transformation. Now we go to the low-pass to high-pass transformation, which is given by the following expression. Here omega c is the cutoff frequency of the high-pass filter on the lower edge of the passband, and Z is new notation for the complex frequency in the S domain to distinguish from S only. It stems from the original, which is from the omega axis. So simply where S is seen, 1 over S is substituted. Here is the mapping. Again, the minimum stop band attenuation and maximum pass band attenuation are not affected. The width of the transition region is again indirectly controlled. Here is the example. Here is a low pass. Here is the transformed solution obtained from the very same original which was discussed earlier. As you can see, the number of transmission zeros is increased by 2, so that the numerator and the denominator are of the same order with 2 zeros in the origin. Here is the result of the mapping. As can be seen, the poles and zeros are now separated. Half of them is in the top part and the other half in the bottom part, and shifted toward the edge of the bandwidth, and of course zeros in the origin are created. Here is the resulting attenuation characteristic. With omega c is now unity. And here is the group delay of the high-pass filter. And finally, the low-pass to bandstop transformation will be discussed. The notation is similar, with the meaning of BR, which is different. Now, BR is a relative width of the stopped band, of the suppressed band, or these filters, of course, are known also as notch filters, but that is mostly associated to the ones which are suppressing only one frequency. Here we are speaking about suppressing of a band. BR is the relative width of that suppressed band. Here is the mapping also shown. So now, as can be seen, two pass bands are created, which are again geometrically symmetric. The values of A min and A max are the same, and the width of the transition regions now is indirectly controlled. Here is what is the mapping creating. Everything doubles again. What is interesting here, zeros at the central frequency of the suppressed band are created symmetrically, of course, which is something specific for this transformation. Here is the mapping of the visualized. As you can see, the zeros are now gathered around the unity and -1. Here is the attenuation characteristic of this filter. Of course, the original is the same for the whole this lecture, and here a relative bandwidth of 60% is used, and also again a careful reader may see that there is geometric, not arithmetic symmetry, with the lower part of the stop band being shorter than the upper part. Here the amplitude characteristic, the gain of the stop band filter, is shown as an illustration of what's going on with this transformation. Here ends the 9th part of the series of lecture. Thank you for your attention.